Okay, it looks like I'm the only one here. I don't know what's going on. Stop video, share screen. We'll share those lecture notes. All right, what I'm going to do is, okay. Somebody just logged in. Hello, Juan, sorry. All right, now it looks like everyone's able to log in. Now I'm seeing people connect. I'm just sending a Blackboard message to everyone. All right, third person logged in. All right, so we're having some technical delays, or we had some technical delays. They seem to be cleared up now, but I want to wait a couple more minutes because people are slowly logging in. All right, so what am I sharing? I want to share my desktop so I can switch. Share that.
Everybody hear me?
Yeah, we can hear you. We're just waiting a few minutes because it seems like Zoom was down a few minutes ago. I couldn't log in, and I see nobody else logged in early, so we're gonna wait a couple minutes for people to join.
Wasn't early, but it said you were in another meeting, quote, quote, and I was still in a room 2 minutes ago, and it was under the same code and everything, but I wasn't with you.
We're all going through a Zoom learning curve right now. All right. Wait one more minute. I'm going to join from my other device just in case. All right, so today is going to be somewhat short. We're going to do basically two things. First, I'm going to go over interference between two sources. Last time, we derived the necessary math for adding waves Now I want to talk about the visual and geometrical consequences of adding two waves that are coming from slightly different points. And then I want to go over a little Zemax exercise relevant to the upcoming assignment. And then that won't be very long. Next week we'll start on a full schedule. Also, in case you haven't heard, it looks like all labs are going to be just online. Originally, we thought some of the upper division labs would be in person, but things keep changing. That's the latest word. I'm sorry for the changing word. With that, let's go to the notes. So we are going to mostly talk about, if I can get to full screen mode, we are going to mostly talk about Young's two-slit experiment, which along with Poisson's spot was one of the definitive experiments for proving that light is a wave. So now we're going to be doing a case where we've got light coming from two different slits. And so this path and this path to whatever point are almost the same. They're not quite. They have basically the same k. If the screen is farther away, they have the same k vector, but they have different displacements r. And so we're going to be adding up two waves with different displacements. Now, what was found in this experiment is even if we have two slits, there is a bright spot in the middle, much like what was found with Poisson's spot, that there's a bright spot in the middle of a shadow. And we see that there are oscillating fringes as well. And these things just could not be explained in terms of a particle model. So if we only had one slit, well, the wave from that one slit would spread out in all directions. And since the intensity goes as 1 over r squared, the field, which is proportional to the square root of the intensity, has to go as 1 over r. And so we just see something that's bright near the center of the screen and dim near the edges. Now there's a very, very important assumption here, an assumption that we'll relax next time. But for now, we're just doing the simplest case. And that assumption is that the slit is very small, so small that if I looked at the path from the top of the slit to our detector or the path from the bottom of the slit to our detector, the difference between those path lengths would be much less than the wavelength of light. Now that's different from the assumption here. Here we're assuming that these two slits are far enough apart that the difference between these path lengths might be comparable to the wavelength of light. But if we're not looking at the two slits separately and the differences between them, but just the differences between points on one of the slits, then these two path differences are much smaller than the wavelength of light, which means that if we're not assuming that the slit size is much less than the wavelength, then we at least have to assume that the slit size multiplied by the sine of this angle is much less than the wavelength of light. And if we can make that assumption, then we can treat all the light from different points on the same slits as just one source. They all add up together. They all travel a distance r1. And then all of the paths from different points on here all travel essentially the same distance r2. So we're adding up two waves, e to the I k r1 over r1 plus e to the I k r2 over r2. And now we have to work with this formula using the methods we developed last time. So the intensity is proportional to 1/2 E star E. So here's the complex conjugate of E. Here's E. We multiply them together and we're going to get 4 terms. 2 of them are simple because we take this and multiply it by its complex conjugate. And we take this and multiply it by its complex conjugate. And those just give us these 2 terms. But then we have terms where the complex phase factors don't cancel out to 1. If we take this term and multiply it by here, we're going to get e to the I k, the difference of the r's. And here we're going to get e to the I k times minus the difference of the r's. And if we add these two things in the numerator, then what we've got is 2 times the cosine of all of this because of this trig identity, or this complex exponential identity. And so we're going to get just 1 over r1 squared plus 1 over r2 squared plus 2 times the cosine over r1, r2. And now here's an approximation that's subtle. This approximation is not always valid, but it is by definition valid in the cases we're considering, meaning that if it isn't valid, then we're not doing that case. If your detector is very far away from the 2 slits, then R1 is very close to R2. So their difference is very small. Maybe 10 to the minus 7 meters or 10 to the minus 6 meters. But let's say that R1 and R2 are at least 10 centimeters. So if we just plug in some numbers, we say that the difference is 500 nanometers. Well, here's 1 over R1 squared. Here's 1 over R2 squared, which differs in the 3rd decimal place. And here's 1 over R1, R2, which differs in the 4th decimal place. And so we can pretend that all of these are the same. Now, we can't do that with the cosine, all right, because you make a small change in this distance, and this cosine could flip from being +1 to -1. So in the cosine, we have to keep delta r. We can't neglect delta r in the cosine, because delta r is changing by enough that the cosine will quite literally oscillate all over the place. And so we get this formula. We get that the intensity is going to be proportional to 1 plus cosine of k delta r. And we're not going to worry about amplitude, about multiplicative factors in the amplitude, epsilon naughts and c's, because all we really want to know is, where are these peaks that people see in the experiments? Even in more advanced work, yes, people will try to fit to the details of these, but trying to fit their data, trying to fit a model to the details of the data, that comes later. The very first thing that everyone always looks at is, where are the peaks, where are the zeros? And then the details come much later. And this is a first optics course, not a graduate level course. So if we do that, then we're going to get that there's a maximum intensity if cosine of k delta r is +1, which means that 2 pi delta r over lambda is 2 pi times an integer, because you get that the cosine is +1 if the input to the cosine is 2 pi, 4 pi, 6 pi, etc. And so you do the algebra and you get that that difference in path lengths has to be an integer multiple of the wavelength. And that just means that we've got something like this, where obviously these distances are much longer than lambda, but this is just to be illustrative. One of these paths, we had 2 oscillations, and one of them, we had 3 oscillations. And so even though they differ by 1 oscillation. So they're at the same point in their cycle. So they add up constructively. And conversely, if the intensity was a minimum, maybe even 0, then cosine of k delta r is -1. So k delta r is either pi or 3 pi or 5 pi, because the cosine is -1 if the input to it is pi or 3 pi or 5 pi, etc. And then you do the algebra and you get that that path difference is half a wavelength plus an integer multiple of the wavelength. So half a wavelength, 1.5 wavelengths, 2.5 wavelengths, etc. And so these waves are a half cycle out of sync. Also, just like in the experiment, we are getting constructive interference at the center of the screen. And that matches up with experiment, it matches up with Poisson's spot, and it's something you simply could not have if light was just rays going in straight lines. You wouldn't have that bright spot at the center of the screen. Any questions so far? All right. Now let's do a little more geometry. If the distance from the slits to the detector is much larger than the spacing between the slits, then we can work in a small angle approximation. This is theta, that's theta, and really, although I've drawn it exaggerated, so this point is pretty far from the center between the two slits, in practice, this distance here would just be much, much larger than this distance here. Then delta R, or delta R is d sine theta, okay? And the reason why that is that we can draw a line perpendicular to both paths. And this is theta. This over here will be 90 minus theta because this angle and this angle add up to 90. And this is part of a right triangle because this line here is perpendicular to the path. So we've got 90 here, 90 minus theta there. The only way these add up to 180 is if this is theta. And then this path difference is opposite theta. The spacing between the slits is the hypotenuse, and so this is d sine theta. And then our conditions for constructive and destructive interference become d sine theta equals m lambda, or d sine theta for destructive equals m plus a half times lambda. And then we can also note that sine theta is just y over L, and as long as y is small, theta is small, tan theta is y over L, but tan theta is also sine theta. So we could write our conditions like this and predict where the peaks are. But even if we didn't do our conditions like that, we could still work out what theta is using d sine theta equals m lambda, and then solve for what y will be. All right, so our intensity is 1 plus cosine of kd sine theta. At this point, a lot of people get confused. They try to do some sort of shortcut in the algebra. They don't want to do all of the steps, but there's no way around it. You have to first compute sine theta. Then you have to multiply that number by kd. Then you have to take the cosine of all of that. You can't do 1 plus cosine of kd theta or 1 plus kd cosine theta or whatever else. These are common mistakes that I see a lot of the time, but you can't do them. They won't work out. Now, what if d is very tiny? Well, kd sine theta is always less than kd. And if d is much less than the wavelength of light, then d over the wavelength of light will be much less than 1. So 2 pi d over lambda will be much less than 2 pi, and so will kd 2 pi d sine theta over lambda. So we're going to be taking the cosine of something that is very, very small. And the cosine of something that's very, very small will never, ever reach the point of being not even 0, let alone -1. So let me illustrate that in a Mathematica file. I'm going to switch gears for a moment. Okay, diffraction of 2 slits. I'll make this Mathematica file available online later. Actually, I'll put it on Blackboard right now. So if anybody is on a laptop with Mathematica installed, actually it looks like I already posted it. So it's available under course documents right now. All right, let me change what I'm sharing. Oh, it looks like I'm sharing the desktop. So you should be seeing Mathematica. I have to run a bunch of commands. If I don't run these commands, if I just have this typed on the screen, well, so far all the Mathematica will be doing is displaying these letters on the screen, but I have to actually go to this line and hit Shift-Enter in order to tell Mathematica, hey, take what's on here and don't just put it on the screen, put it into your memory. So that whenever you see the command intensity 1, that means this. And then I have to run this and say to Mathematica, hey, whenever you see the symbol lambda or the symbol k, put these things in their place. All right, so now let's look at that. What we're plotting here is intensity versus angle. And I'm controlling what range of angles. So right now I've got the spacing of the slits at 0. So no matter what angle I look at, I'm not seeing anything. But then I do this. All right, I start playing with spacing between the slits. And what we see is that the number of peaks on the screen, on the detector, and the number of zeros on the detector, those start to increase as we increase the slit spacing. Because as we increase the slit spacing, we're increasing D. And if we increase D, then as we vary the angle, D sine theta can cover a wide range of values. Sine theta is going between 0 and 1. So if sine theta is going between 0 and 1, then D sine theta is going between 0 and D. And if D sine theta is going over a larger range, then KD sine theta is going over a larger range. And as KD sine theta goes over a larger range, well, we're taking the cosine of KD sine theta so we can see more oscillations. Can anybody tell me what's one thing that's unrealistic about some of this right now?
All the intensities as angle increases are the same.
I'm sorry, I couldn't hear you.
The intensity doesn't decrease as angle increases.
Yeah, so let's work that out. I'm gonna switch to something where I can handwrite. So let me go into Zoom on my device, and I'm going to share this whiteboard. Can people see me scribbling right now? Can people see that?
Yes.
You're seeing Mathematica.
What? You're still seeing Mathematica? Okay, so I think what we gotta do is go to, there was something I had to do in settings.
I'm still watching your white screen. I saw your scribbles.
Yeah, there's something I got. Okay, so some of you see my white screen. I need to...
Yeah, Patrick helped me out. Now I can see the scribbling. Thank you.
There's supposed to be a way... Oh, okay, so you guys are doing a group chat to go over, I see. So there's a group chat to see whose screen you're seeing. All right. So on the whiteboard, this is theta, this is R. We're going to say that L is 1. So what we've got is that L equals R cosine theta equals 1. So R is equal to 1 over cosine theta. And then 1 over R squared is equal to cos squared theta. Any questions on how I did that? All right, so then let's go into Mathematica again. Let me make sure I'm still sharing Mathematica. So now switch to my other thing. And I'm going to put a parentheses. All right. And when I do that, then we see that it indeed,
I
even
can't see
if
your
we
Mathematica
just
screen.
have the one item, oh, you know what I did? I forgot to multiply the whole thing by cosine squared theta. I only multiplied the second term. All right.
I still can't see your Mathematica screen, but I'm
What?
on an iPad, so I don't know how to change that.
What'd you say?
I still can't see your Mathematica screen. I'm still on the whiteboard screen, but on an iPad, I have no idea how to change that.
All right, let me see what I can do. I should be sharing just this.
Yeah, because there's no view options button on an iPad.
What?
There's no view options button on an iPad.
There's no view option with the Mathematica screen?
No.
See, sometimes this works and sometimes I still haven't figured out how it is that I toggle the setting between having two people share their screen or just one, or having two of my logins share the screen or just one. When it's down here, meeting controls, let's try video settings. No.
Yeah, so what I'm experiencing is there's two logins of you, so there's two Alex small screens, but when I go into either one of them and select the C screen share, it still goes back to the whiteboard.
Okay, so what I'm going to do is I'm just going to temporarily log out my other device, and we'll see if that helps.
Now I can see it.
All right, now you see Mathematica?
Yes, sir.
Okay. So when I bring in that 1 over r squared term, then I get something that is a little more realistic. But still, the key thing is that you see more oscillations if you have a larger value of d, and you see fewer oscillations if you have a smaller value of d. And this is part of why it is that it took so long to do this, because if we have too many oscillations, we have too large of a value of d, we're going to get so many oscillations that it'll be hard to actually notice the spacing between them. And plenty of objects in the macroscopic bulk world give us that effect. Whereas if we have too few oscillation, if we have too small of an object, like say the molecules of gas in the air, then we aren't going to see even one oscillation. We're just going to say very small, and all we're going to see is this, which only goes to 0 because of the distance. But we'll never see, we have to get to a certain size before we notice any deviation from that 1 over r squared. And that 1 over r squared could have been predicted if light were particles bouncing off in all directions. Then it would be just like light spreading out in all directions. And we know that when we calculated the intensity of light spreading out in all directions, we got 1 over r squared. All right. Other things we could do. We could ask what happens if we have more than 2 slits. Well, if we have just a finite number of slits, we just generalize what we did before. We calculate the field from slit 1 using distance r1, the field from slit 2 is distance r2, and then do the same with distance r3 and so forth, and we add them up. If we had an infinite number of slits getting closer and closer together, what do you think we would do?
An integral.
Yeah, we would do an integral, which is what we're going to do next time. Let's also talk about the width of the central peak. We get our first 0 when d sine theta is lambda over 2. We get a half cycle difference. Oops. Well, that means that sine theta is lambda over 2d. So the width of this peak is proportional to sine theta and inversely proportional to how far apart the slits are, which is similar to what we are going to find next time when we talk about a finite size slit and we do the integral, and we're going to get the same thing, and that'll be directly related to what we found last week in Zemax when we played with wave optics in Zemax and found that the width of the ripple pattern was proportional to the wavelength of light divided by the aperture. And that just comes from the fact that when the sources of interfering waves are farther apart, the angular width is smaller. And the wider the lens, now the lens is giving you an infinite number of interfering waves, but still, many of those waves are further apart from each other. So again, they produce a narrower central peak. Something else that's going to matter when we get to modulation transfer functions next week and after spring break. Let's say that we had a wave coming in at off normal incidence. So instead of just having the light coming in like this and like this, because if we had the light coming in like this and like this, then whenever a peak reaches this slit, a peak reaches that slit, and vice versa. And when we do that, the only path difference we have to worry about is over here. But now we're having them come in off normal, so there are 2 delays. The waves that are hitting this one get there later. The waves that are coming from this one get here later. So there's a delay up here and a delay down here. And the whole question is, what is the difference between those delays? And the math is pretty much the same. We already know that this leg here, this extra distance, is d sine theta 2 is what we're now going to call it, because it's the angle over here. And over here, let's see, this is theta 1. So this is 90 minus theta 1. So this, sorry, yeah, theta 1, 90 minus theta 1. So this is theta 1. So this difference up here is d sine theta 1. So we have that d sine theta 2 minus d sine theta 1 equals m lambda for a peak. Well, let's divide both sides by lambda and multiply both sides by 2 pi. And now what we've got is, and we'll divide both sides by d. So now we've got 2 pi sine theta 2 over lambda minus 2 pi sine theta 1 over lambda. And those look a lot like the y component of the k vector, because the length of the k vector is 2 pi over lambda, and the y component of the k vector would be the length multiplied by sine theta. So what we've got is ky over here minus ky over there equals an integer multiple of 2 pi over d. 2 pi over d is something called a spatial frequency, all right? You've probably learned in math methods that you can take periodic functions and divide them up into sines and cosines via Fourier series. And you can take non-periodic functions, and as long as certain facts about their integrals hold true, facts that just about always hold in optics experiments, you can break them into an infinite number of sines and cosines via a Fourier transform. And what you're doing is you're basically breaking them up into sines and cosines with different frequencies. Well, here we've got a transmission function, all right? Transmission is a function of y. And the transmission is 0 in most places. But here and here, the transmittance, the fraction of light getting through, is 1. And if you were to take the Fourier transform of this, you would get a function that oscillates as a sinusoid, all right? And you would get that the strongest peaks in that Fourier transform are at integer multiples of 2 pi over d. And so what's happening is that when you send in waves and they hit something and they spread out, their wave vectors get shifted by integer multiples of the spatial frequencies that are present in here. All right, so the strongest transmittance happens if the wave vector got shifted by a spatial frequency that's in here. And we'll do more on that next week with modulation transfer functions. But I just want to give you a little taste of that. And if you really want to learn all about this, you should read a book called Fourier Optics by Joseph Goodman, which is like the Bible of Fourier optics. We'll do a little more Fourier optics with modulation transfer functions, and then a little more Fourier optics when we get to diffraction gratings. But what you're going to find again and again is that spatial frequencies matter a lot. The strongest interference or diffraction, the strongest effects when waves spread out and add up, happens when wave vectors get shifted by integer multiples of the strongest spatial frequencies in here. Any questions at this point? Okay. Then we are at the end of this part. I want to switch now to Zemax. All right, so if you are in front of Zemax, then open up any file that has, and I'm going to move a copy of this to my other folder while I'm going to Zemax. Open up any file that has a plano-convex lens in it. All right. Or you know what? I'm just going to go into single thin lens, test here, and make it a plano-convex lens if it isn't already. We just need a plano-convex lens. And I just realized I'm not sure what Zoom is sharing. It's sharing my desktop. Okay. All right, that's a plano-convex lens. Now, let's make it so that this first layer thickness is infinity. That's fine. We will change the fields to get rid of object height and make it angle. And we'll go to layout and we will optimize and do a quick focus. So what we've got right now is a single thin lens. It's plano-convex, and we see 3 spots. And if we look at our spot diagrams, what we want to do is we want to compare with the ideal case. And to compare with the ideal case, We have it show the airy disk, which is what you would get if it was a perfect lens with the size, with the aperture opening that we've allowed this to have. And we see that they're pretty small compared to the airy radius. So right now, aberrations aren't going to matter. Let's make aberrations matter. All right, and let's do a quick focus. All right, aberrations matter a lot here. Actually, let's go down so that aberrations are slightly less important. By the way, do you notice how when it's out of focus, you see effects like this, almost like a globe bulging out? That's how I can immediately look at spot diagrams in your assignments and realize that you did something wrong. Because if I do a quick focus, it switches from that to this. All right, now we know, what do we know from a few assignments ago about a plano-convex lens with light coming in from infinity? What do we know about the orientation of that and the image quality?
It's better if you have the plano-convex lens oriented just as you do.
Yep, it is better if we switch around. So let's take one more look at the spot diagram. Make a note of this size. Right now, the RMS radius is 27 microns. Now let's go into the lens data. And this is 10.0 or minus 10.0. So let's switch that to be 10.0. Now let's switch that to be infinity. And then let's take a look at our layout. And let's take a look at our spot diagram. And do you see how it dropped? Right? You see how the spot size dropped? And that's even before we did a quick focus. And then we do a quick focus, and it drops again. At this point, it is only 3 times the airy radius, which is the fundamental limit, whereas before it was about 12 or 13 times the airy radius. So what we see is that something we already knew, but now let's compare the diffraction and circled energy graph. Okay, for the on-axis, which is the blue curve, we get 50% of the energy at a radius of 3.464. And yeah, 3.464. I'm going to write that down for myself. So now let's switch it back to the previous orientation. So we'll make that infinity and that minus 10. Always check the layout. Do a quick focus. All right, now let's see where the 50% is. And the 50% is at a radius of 20. So what we're seeing is that not only do the geometrical optics calculations get worse when the aberrations are worse, but the wave optics calculations get worse too when the aberrations are worse. Any guesses as to why? Well, aberrations are deviations from ideal. Fine, aberrations are bad, but saying that they're bad, the aberrations were calculated in a situation where we weren't talking about waves. But there was one concept in geometrical optics that ties in with waves, and that was the principle of least time. Because the idea in the principle of least time is that if all of these paths, if everything is working, all of these paths will take the same amount of time, whether I go this way or that way, all of these paths should take the same amount of time. Now, if all of your paths take the same amount of time, then what do we know about the phases of the waves arriving together from what we just discussed?
They're in phase.
Reconstruct.
What? What?
They're in phase and lead to constructive interference.
Correct. If they're in phase, then it should be constructive interference. And so aberrations are basically telling us that we are deviating from the principle of least time. All right, we are deviating from that goal of having all the waves take the same amount of time. We are deviating from that goal of getting constructive interference. All right, and so what you're going to find when you do this for next Tuesday is that you've got two different orientations. And one of these orientations gives you worse aberrations, and that same orientation should also give you somewhat worse behavior in the analysis you're going to do. And it's because even though geometrical optics and wave optics are on the surface very different ideas, the one thing that ties them together is that you get your best focusing of light if all of the paths take the same amount of time. It's the one place where these two subjects make contact with each other. And so anything that gives you, any lens orientation that gives you better behavior in the geometrical optics regime will almost certainly, I'm going to say almost because there's always some clever exception that someone's thought of and I haven't, but almost always give you better behavior in the wave optics regime as well. Any questions? Okay, so if we were in the computer lab, what we would do right now is we would take a 10-minute break, and then you would go and work on Zemax, and I would take questions. So at this point, I want to take a break and get a cup of coffee, and I will be back in 10 minutes. And if you're still logged into Zoom or you log back into Zoom and you want to ask me Zemax questions or questions about anything else on this, I'm happy to take those questions. Otherwise, as always, I'm available by phone or email. And next Tuesday, we will be doing a little more in this time. Next Tuesday, the second half of class will not just be for you to work and ask questions. I'll actually have some additional things to go over, some Zemax activities. Who's annotating my monitor? I didn't know that you could do that. Well, thank you for the smiley face, but I had no idea that someone else could annotate on my monitor.
We all have access to it.
Sharing options in. Nice. All right, gentlemen, I'll see you in a little bit, but right now I really need some coffee. Be back in a few. All right, I'm back if anyone has questions. Be around.